In this course, we're going to ask you for more than just memorization of facts and repetition of ideas that we give to you. We're going to emphasize deep conceptual understanding of large biological principles, and we're really going to emphasize the interconnectedness between the information and ideas that we're talking about to form a much larger picture. And a very good way of visualizing that in a way that's very easy to digest is building a concept map that shows how all of this information and these ideas are related to each other in this interconnected web. So the purpose of this web lecture is to familiarize you with the idea of concept maps and how to build them, give you a couple of examples, and show what we expect from the various concept mapping activities we're going to be doing this semester. So what is a concept map? A concept map is a diagram that shows a certain number of facts, ideas, concepts with connectors or links that show how they're all related to each other. So these types of links can be a cause and effect relationship. The thing in the first bubble causes the thing in the second bubble. They can be inclusion. These are three things that are included under this larger idea. They can be characteristics of the thing that's in the bubble. They can show action, parts of a process, a sequence of events in time, or show how things are similar or even how they contrast. So we've got a very simple example here, looking at the states of matter. So as we know, matter has three states, and this arrow indicates that we're going to be using water as an example. And we see that the three states of water are a solid form, which is ice, a liquid form, which is water, and a gaseous form, which is steam. And which form the water will take will depend on the temperature. This is also related, as we know from chemistry, to the pressure. And we also know that this is purely a physical change and that the chemical structure of the water remains the same. It's still the same thing, H2O, just the molecules are connected to each other in a very different way. So this is a very simple one. Let's take a look at how we would build a concept map like this. And we're going to use as an example the very familiar ideas from any science classes that you may have taken, the relationship between facts, hypotheses, theories, and laws. So we've got these big ideas in bubbles separated from each other. Now we're going to start to think about how they're related to each other. So facts are direct observations, things that we can actually observe ourselves or measure in some way. So these are the outcomes of experiments. These can be just observations that you make, things that you see with your own eyes, measure. Facts are not anything that happens to be true, right? Facts are a subset of things that are true, things that are directly observable or measurable. So how are these related to hypotheses? Well, the observations that you make might lead you to wonder what's responsible for that observation. It might lead you to propose explanations. That possible explanation is a hypothesis. Right? This is one possible reason that might have happened. And of course, you can develop an experiment to test your hypothesis, maybe against some alternate hypotheses. And the results of those experiments are going to generate more facts. The results of those experiments are additional facts. So testing hypotheses generates more facts. So if you test a lot of related hypotheses, they may suggest to you a much broader principle that explains a large range of phenomena and allows you to make predictions, and that would be a theory. So consistent results from testing many related hypotheses may lead to the development of a theory, a general explanation for a wide range of phenomena under whatever conditions are covered by the theory. So theories, in order to be theories, must have predictive power. So that theory is going to allow you to generate more hypotheses, right, in the form of predictions of the outcomes of experiments that will either support or fail to support the theory. If they fail to support the theory needs to be revised. So what is a law? So the theory is going to propose some mechanism, some mechanism that explains why these facts, why these outcomes of the experiments are true. If that mechanism can be described by a mathematical relationship. That mathematical relationship is a law. So basically, a law is the mathematical description of a theory. That's how they're related to each other. And we know for both theories and laws, all observations need to be consistent with those theories and laws. If any of these observations, any of these facts that you gain from testing hypotheses, from doing experiments, are not consistent with the theory or the law, the theory or the law needs to be revised to take into account these new observations. Theories and laws have to be consistent with all known observations that come under their purview. So that was a relatively simple example with just 4 bubbles related to each other, but we can also use this method to summarize entire topics. The example I'm going to show you is from the general biology textbook about the origin of life on Earth and the conditions that were necessary for life to have emerged from non-life. So we're going to have physical factors that had a role to play. We're going to put those up on the top part of this circle, and then we're going to have the biochemical reactions that are necessary to form life on Earth, and we're going to put those down on the bottom. So let's start with the physical factors. So one thing that we know that we need for life on Earth is moderate temperature. We know that biochemical reactions occur within a narrow range of temperature, and so we need to be in that temperature range for life to have emerged. We also know that liquid water is very important. Biochemical reactions occur in aqueous solutions, and so liquid water is necessary for those reactions to happen. And these two are, of course, related to each other because at lower temperatures, more of the water on Earth is in the liquid phase rather than the gaseous phase. So how did we start getting the temperature reduced on Earth? Well, early in the Earth's history, the Earth was being bombarded constantly by asteroids. This began to slow down, and so the Earth was not constantly being heated up by these impacts from asteroids. And then, as a result, heat was given time to radiate away from Earth and out into space, and so the temperature at the surface was able to cool down. And this is also related to the reduction of carbon dioxide levels in the atmosphere on Earth. The level of carbon dioxide is related to the acidity level in the water. We'll see why in just a moment. And we also know that biochemical reactions occur within a narrow range of acidity. And so it was very important for the carbon dioxide levels to be brought down and stabilized to allow these biochemical reactions to take place. So let's take a look at how that happened. We can see this in diagrammatic form. We have a lot of carbon dioxide in the atmosphere. At lower temperatures, we start to get clouds forming. Remember, clouds are condensed water in the atmosphere, so these are little water droplets. This is not evaporated water or water vapor. This is actual liquid water up in the air. The carbon dioxide combines with that liquid water in the clouds to form carbonic acid, which then falls as acidic rain. That acidic rain falls on rocks, mountains, and the acid dissolves a little bit of that rock every time it comes in contact with it and breaks that rock down into calcium ions and bicarbonate ions. Those ions are then carried down the mountains in rivers out to the oceans. In the oceans, the calcium and bicarbonate ions precipitate to form a rocky substance with very low solubility called calcium carbonate. This is the material that most marine vertebrates build their shells out of. So this is not a very soluble substance. So that carbon is then trapped in the ocean. It doesn't return very readily to the atmosphere. And so it's sort of a one-way street for the carbon from the atmosphere down into the clouds, into the acid rain, down the river, precipitating out in the oceans where it's sequestered and stored more or less permanently in the oceans. So how can we represent this in our concept map? Let's take a look. So we've got liquid water, which combines in the clouds with atmospheric carbon dioxide to form carbonic acid, which then reacts with the rock to form the bicarbonate and calcium ions. The carbonate and calcium ions are carried by rivers to the ocean, which then precipitates to form not very soluble calcium carbonate. So it's stored there in the oceans, not returned to the atmosphere. So we get that reduction of carbon dioxide. But this is not the end of the story, because we also know that the level of carbon dioxide in the atmosphere is related to temperature. We know about greenhouse gases. So when there's a lot of carbon dioxide, the heat is stored in the atmosphere. When there's less carbon dioxide, it's released out into space. It's able to radiate away. So this further reduces the temperature on Earth. And so now we've got a cycle here between reduction of carbon dioxide levels, which continues to decrease the temperature. You get even more liquid water that takes us back into this one-way street for carbon from the atmosphere down into the rocks at the bottom of the ocean until such a point as the carbon dioxide levels are stabilized so that they're not having a large effect on the temperature anymore. So those are the physical factors. Let's start to think about biochemical reactions. So first, of course, you need organic molecules. Where did these organic molecules come from on Earth? Well, there are a few different theories about that. One is that there was a reducing atmosphere on Earth with these chemical compounds present, which basically is all the ingredients for organic molecules, and all it really requires is an energy source to start building these into more complex molecules. The possibility is supported by a series of experiments that began with the Miller-Urey experiments, which combined all of these elements, these molecules in the reducing atmosphere, exposed them to a source of energy, and found that they did, in fact, begin to form organic molecules. Another hypothesis is that organic molecules arrived here from space. So these two possibilities are not mutually exclusive, but we do have some evidence of extraterrestrial presence of organic molecules we find in meteorites. Specifically, the one mentioned in the textbook is the Tagish Lake meteorite, where we find evidence of organic molecules inside that meteorite. So another thing that we need for life as we know it on Earth is there's got to be metabolic pathways. We need to be able to convert chemical energy into usable energy to be able to support life's processes and maintain homeostasis, conditions inside cells that are different from the conditions outside cells. This is what we call homeostasis, and that takes energy. We need to be able to convert energy to be able to use it. So obviously there need to be organic molecules before you can have metabolic pathways. But where do these metabolic pathways come from? Possibly we began with some form of autotrophy, building organic molecules from inorganic compounds, and the energy source for this might have been converting formaldehyde into glucose as an energy source and using glycolysis. But of course, glycolysis requires enzymes, and one possible source of those enzymes could be RNA. So RNA is, of course, closely related to DNA. It's built from nucleic acids, just like DNA. Because RNA is a much simpler molecule, it probably preceded DNA as the original genetic material. But we also have found out that RNA works very effectively as an enzyme and could have done so before amino acids existed, before we could build simple protein enzymes, which is what performs that function in living organisms now. So RNA could have performed both of those functions, being the genetic material and also catalyzing these enzymatic metabolic reactions. The other thing that was needed for life on Earth was the presence of a cell membrane. The cell membrane functions to separate the cell from the external environment so that conditions can be maintained within the cell that are conducive to life processes. So what do we need to be able to have a cell membrane? Well, we know that now cell membranes are composed of phospholipids that form a bilayer with hydrophobic and hydrophilic regions, but that's a very complex molecule. Is there a simpler molecule that might be able to perform the same function? Well, possibly fatty acids. So it turns out that fatty acids have hydrophobic heads and hydrophilic tails and can form little bilayer bubbles that could contain these biochemical reactions that allow homeostasis to be maintained. So this is a summary of a big chunk of the chapter in the general biology textbook on the beginnings of life on Earth. And so this is the kind of web of understanding we hope that you will begin to build, so you can see how all of these things are connected to each other, how they're related to each other. So when you actually do this, either for studying or for your assignments, just having this framework is only the first step, figuring out how they're all connected. You also need to be able to explain all of those connections. So the next step is to number every single one of those links between ideas and write a little something about the nature of that relationship. How are these two things related to each other? And I've written up examples of what you might say for each of these. I'm not going to go through everything, but I will post this PowerPoint so that you can go over this example at your leisure. But basically, it's just a sentence or two that explains the relationship between those two things. But it's still enough so that you make sure that you're absolutely clear in your thinking about how these things are related to each other. You can articulate it, you can communicate it, but then also you can go back and remind yourself, what was it that I understood when I built this concept map about the relationship between these two things? Am I going to remember what I was thinking? So if you have a written record, then you can go back and say, okay, now I remember what I understood about how all these things are related to each other. So that is the basics on how to create a concept map.